Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing about olefin polymerization in the last few lectures. In this regard, we have covered several topics including polyolefin classifications from a material perspective, like types of different types of polymers that can be obtained from polyolefin polymerization based on their properties, the polymer material properties, like something which is elastic, something which is plastic, something which depends on duroplast, depends on temperature, so on and so forth. And we have also looked into polymer characterization based on the processes, for example, the condensation polymers or addition polymers, the reaction they use for making these polyolefins polymers, as well as we have distinguished or classified polymers based on the mechanism, step growth mechanism and chain growth mechanism. And we have also looked into the polyethylene from the perspective of their different types, classes of polyethylene polymers that are known, to the historical perspective of their development from Philip process onwards to nickel effect, and then subsequent discovery by Ziegler to produce high density polyethylene at room temperature under 1 bar pressure using titanium as catalyst. Now, moving on, we have also looked into polypropylene polymerization polymers, and polypropylene was polymerization of propylene, which was mainly been attributed to the development by Julia Natta. And we had seen that how polypropylenes polymers are different from the polyethylene polymers, mainly from the orientation of this methyl side chains of the propylene group, which can be atactic, syndiotactic, stereoblock, hemi-isotactic, so on and so forth. Today we are going to go deep, delve deep into this polypropylene polymerization, particularly from the mechanism and the catalyst development point of view. Now, polypropylene so this is Ziegler-Natta. Now, a catalyst gives isotactic polymers. This has two main issues with it. The first is that why isotactic polymer, which means that all the methyl groups are on the same side, stacked on the same side. They all appear in the same side, and overall they sort of become chiral. All the carbons have the same configuration. And these sort of led to two questions regarding the mechanism of polymerization with Ziegler-Natta catalysis. The first question being Y is polypropylene produced in Ziegler-Natta process isotactic. Now, this is a important question, because it says that how come a polymer which is chiral in nature and isotactic in nature produced from a catalyst which is achiral or non chiral. So, there is a element of suspicion as to how come achiral catalyst produce chiral product. This is a counterintuitive question which does not satisfy the intuition that one can obtain isotactic polymer from just TiCl4 and diethyl aluminum chloride, which is the Ziegler-Natta catalyst, which itself is a achiral. So, this is the important question which throws out some more insight into the process of polypropylene polymerization under Ziegler-Natta condition. And the second thing which comes out of it is how does head to tail linking of propylene monomer occur. So, this also is important question, because head to tail linking means that all the monomers are sort of linked in a same fashion. So, if this becomes the head and this becomes the tail. So, this is head, this is tail, this is head, this is tail. So, head to tail linking, head to tail linking happens all the time. Resulting a polymer of this type, whereas there can be possibility of tail to tail, head to head, other possibilities they do not occur. So, these questions throws out important challenges on the mechanistic part that should explain why such thing is observed. Now, the mechanism for polyolefin is best given by a mechanism which is called Ullmann-Cosse mechanism. Which was given in 1964, and which states that free coordination site cis to a titanium carbon bond is crucial for the polymerization. Now, this at this juncture with this information, this Ullmann-Cosse reaction mechanism does not explain the full or explain both the questions we had posed earlier about the isotacticity of the polymer polypropylene or about the head to tail, but this sort of explains the second part, the head to tail mechanism arising out of this process. And it says that head to tail results it says a sequence of head to tail linking results in chain growth, beta hydride elimination, which causes chain termination. So, let us they explain this Allman-Cosse conveniently explain that the presence of a vacant bond, the vacant site next to a growing alkyl chain is essential for the head to tail insertion resulting in the polymer growing polymer chain. But what it does not still yet explain is the reason for isostactic polypropylene that is observed during the Ziegler-Natta polymerization. So, let us just see the second aspect first, that head to tail arrangement through the mechanism as is shown over here. So, H 3. So, this is the vacant site which is occupied by an olefin So, this is this insertion step on this vacant site occupied by this ethylene, resulting in a polymer chain on this arm and a vacant site on top as is shown here. So, now the polymer chain has moved now the polymer chain has moved and there is a vacant site over here, and that then gets occupied by another polyethylene molecule, and the reaction then proceeds further. So, the point to note is two things. One is that first thing is that there is a vacant site cis to the titanium carbon bond, followed by this vacant site being occupied by this propylene, and then the insertion of this propylene unit into the bond. As a result, this alkyl chain now shifts to the side and another vacant site is created, to which this olefin now comes and bind. So, this is called migratory insertion. There is a migration of the alkyl chain which happens from this to this. So, and as a result, if one were to take a look that because of this oscillatory migratory insertion, there is a head to tail joining of the propylene unit. So, all the methyls are pointing towards the same. So, this explains the second question, that this propylene is formed in a head to tail fashion, but still a lot more remains to be answered. The first question, that why is it isotactic? Isotacticity would depend on the stereochemistry of this carbon. These are all carbon attached in a head to tail fashion. Tail linking of propylene, head to tail linking of propylene, and then the isotacticity would depend on the configuration of this carbon, and for that to happen, then the catalyst have to be a chiral in nature, and that can be explained, this atacticity explained by the fact that the stereoselectivity of the Ziegler-Natta catalyst is enhanced in magnesium support, which are to be considered in more details. So, to explain the chirality, one needs to consider the fact that there is a huge increase in activity and stereoselectivity by anchoring the Ziegler-Natta catalyst to a magnesium chloride support. Okay. Now, this is something which is important observation, that Ziegler-Natta catalyst when attached to magnesium chloride provides isotactic polymers, which sort of indicates that there some amount of chirality in the catalyst, supported catalyst, is brought about by anchoring the Ziegler-Natta catalyst onto a magnesium support, and we are going to explain that. And the second thing which also comes into play is that acoustic and acoustic C alpha H to titanium. So, acoustic interaction between C alpha alpha carbon alpha proton to titanium interaction may promote stereochemical fixing of the polymer chain and bond reorganization during the insertion step, and the bond reorganization during the insertion step. And this more specifically is explained by the fact that the origin of stereoselectivity arise from chiral titanium site that allows enantiofacial differentiation during coordination of propene and this chiral occurs by alkyl titanium unit in octahedral environment at a MgCl2 crystal surface. Now, this is a very powerful statement. It explains the nature of isotacticity. It says that the origin of stereoselectivity arises from a chiral titanium site which allows enantiofacial differentiation during the coordination of propane, and that arise by the titanium alkyl unit present in octahedral environment in a magnesium Cl2 crystal. So, it says that when titanium alkyl unit of Ziegler-Natta catalyst with growing polymer chain is present on a magnesium Cl2 crystal, then the overall the site the catalytic site becomes chiral and results in isotactic polymer. So, this can be best explained by the orientation as is shown over here, titanium Mg these are chlorine Mg chlorine So, this is the polymer chain, and here is the vacant site. This is the vacant site and this is the polymer chain. Now, let us draw this configuration similarly. As is shown here. Mg this is the polymer and this is the vacant site as is marked over here. This is the polymer chain and this is the vacant site, and this is how the titanium is supported in the magnesium chloride crystal, and these are chiral titanium site, chiral titanium site. Now, when the olefin comes, then the binding of olefin happens in this fashion. As opposed to because of obvious reason, this one is favorable binding. This methyl group and this polymer chain are further apart. Unfavorable binding, because now the methyl chain are these are sterically hindering, and as a result these results in facial discrimination of results in facial enantifacial discrimination in propene binding coordination, giving isotactic polymer. So, this is a very important concept which is shown that this binding is unfavorable, favorable this facial binding and that leads to enantifacial discrimination, whereas this is the interaction between this is not favorable and that gives rise to isotactic polypropylene. So, with this we come to the conclusion of today's lecture, in which we have explained the result of two things which are not very obvious from the Earl-Minkowski reaction. First is the head to tail linking of the polypropylene, linking of propylene in polypropylene polymer, and this is explained by the fact that there is a vacant site cis to the growing titanium carbon bond of the polymer chain. And second thing is the isotactic polymer, the chiral polymer being obtained from Ziegler-Natta catalyst, and this has been attributed to a chiral site by formation of the titanium on the magnesium chloride crystal, which results in a chiral environment around the catalyst, and that successfully carry out enantiofacial discrimination of the binding propene, which result in isotactic formation of the polypropylene. So, with this we come to an end of this today's discussion on polypropylene. More on the perspective of this interesting chemistry of polypropylene as we meet in the next class. I once again thank you for being with me in this next class. More of the exciting stuff coming up in the next class, where we see the catalyst development and walk you through the various aspects of polypropylene chemistry in terms of catalyst design and polymer activity when we meet next. Till then, goodbye and thank you.